Welcome to this session of the Monte Carlo lecture, in which we will talk about a few other methods of generating data from given distributions. To start, let's ask about generating data from truncated distributions. And what we mean by that is, suppose that I have a distribution that I want to draw from, and what I really want is not the full distribution. I actually want, redraw that a bit. I actually want part of the distribution, so I'm truncating it here. I don't want this part. All I want is a draw from this distribution. One method to do this is an accept-reject method. It's very straightforward. You draw from the full distribution and you throw out the values that are on this end of it, and you keep the values in the range that you want. It's very straightforward. Draw from S, keep X if it's in, I draw from F, keep X if it's in the range. This is not very efficient because you're throwing away a lot of data that your computer is in fact generating, particularly if you are looking at really small areas. This is where you want the data, and this you don't want. You're going to get most of the computer's work is going to be drawing these, which you're just going to throw out in the trash bin. But this is a way to get truncated distributions if you need to, and if you can afford the efficiency, which might not be so bad if your truncated distribution is out here where you're throwing out an upper tail or a small section. Another accept reject method, which is a little more general, is to identify that although you want a distribution from F, you can't draw directly from it, let's suppose, but you can draw from a distribution G. You draw from G a set of x's, you draw a set of uniform variables, and then you have a scale factor m, which I will mention in a minute what it is, such that you will keep xi if that uniform variable is less than the ratio of the density under f of x to the scale factor times the density under g of x. Here's the idea. For the moment, let's suppose that n is 1. So right here, this just is simply g. Well, let's suppose that I were able to fill out a histogram of data so that it fills out this, this curve of g. So I've got data stacked all the way up here for each of these. So I've done a huge random draw from g. Now if I took each x point and I kept it with the probability associated with the proportion of f to g, I will keep this fraction of it. And at this point here, I will keep this fraction of it. Or in other words, I will throw out that amount of it, leaving only the below. I will throw out this amount up here. And eventually, you will throw out all of this portion, keeping just the histogram of data under F. And that would be a sample under F. That's the idea. Now, M allows us to take a distribution that may actually start below, and this would be bad because we've got higher than this, we can't do that, and inflate it and blow it up by multiplying G. So if this were G, multiplying it by M so that we get a distribution that essentially covers the distribution that we are interested in. And the scale factor M you want so that it covers it all the way out in the tails, and it does so as minimally as possible, which means you want the distance to be as small as possible. But it still has to cover it all the way out in the tails. In other words, your mg must go above however f is actually going. The key is if you make it too large, you're going to be throwing out too many, and you don't want to throw out that much. Another way is called importance sampling. Let's suppose you want to calculate this interval, but you cannot draw from that distribution. However, you have some other distribution that you can draw from. Well, if you multiply and divide by h, so I'm multiplying and dividing, I'm not changing anything in the integral, in fact. It's just multiplying divided by 1, multiplying by 1 by multiplying divided by the same thing. And so that gives us a new integral of g times f divided by h. And here I've converted this into the notation of df of h. So I now need to draw from f of h, which I said that I can draw from, right? I said I could draw from it. And I calculate this new quantity, and I get the sample average, and I come up with an estimate for this distribution. Straightforward. I've drawn my x's now from where the distribution h that I was able to draw from. I calculate the value for each of the x's. I take my sample average, and that gives me my estimate. Turns out that it's not necessarily very stable. It has to do with this ratio here, and we'll talk about that in a moment. In general, what this requires is that the support of the distribution f that you're interested in is contained in the support of h. So if for some reason h is bound to here and you're interested in something outside of that, well, it's not going to work well because the support of f is outside of the support of h. So you need the support of f to be contained in the support of h. You also need that the ratio f over h is finite for all x's. What that means is, particularly in the tails, that the limit as x goes to infinity on a continuous space, that this does not go to infinity. This would be bad. We don't want that to happen. So you need a good candidate for h so that it behaves well relative to the distribution that you're interested in. But because of this, this can generate a lot of variance. So there's a way to stabilize the variance. The way to stabilize the variance is to create a weight, which is what we call the ratio of f to h, and then sum those weights across all of the observations that you've drawn, the random draws you did, so that you can essentially get a normalized weight. And now you sum the random draws of your function with respect to that ratio normalized by this sum. This is much more stable in terms of the variance. It is, however, slightly biased. So it's a bit of a trade-off there. Again, you need a good candidate for h, a good what's called proposal distribution. And that depends a lot on its relationship to f. Like I said before, it needs to cover the support of f, but it also can't be in its relationship with the ratio to f such that the ratio goes to infinity. Now, quite often, this importance sampling can be very useful, but sometimes when people jump to it, I've noticed at least that you could just as well do a uniform variable transformation the way we've done it before, and this will be much more precise than will be importance sampling. So if it's possible to do the simple uniform transformation, then I would recommend that over and above using importance sampling. The advantage of importance sampling comes when you want to put information in a very specific area. Again, we're talking about integrating over a certain section of a distribution. It might become important there. Now, during this whole time, we're talking about drawing samples from a distribution, and you essentially can get variation, right? And so here's 4 different draws, and they vary. And this one looks a little clustered here, and up here this one's not. And we've got more up here than we got in this draw. And so each random samples vary. This is nothing surprising. So the question is going to be, can we do better? Can we find a way to reduce this variation? And that will be the topic of the next video.